Okay, moving on from statistics, we're now looking at probability and the standard normal distribution. Okay, so after today, you'll be able to calculate probability for simple events, understand concepts related to probability distributions, and know key concepts and characteristics of the standard normal distribution, which involves reading z-scores from a table and calculate related probabilities. So just a little bit about probability and the standard normal distribution. The probability for simple events, you have a full range of things that can happen. An event can be impossible to occur, in which case we say that it has a 0% probability, or it can be certain to occur. So I'll highlight that. So we have impossible at one end of the spectrum and certain to occur, which is where it's 100%, or written as a decimal, it has a value of 1. And within those two ranges of values from 0 up to 1, we have moved from unlikely to where there's an even chance of events occurring, 0.5. And then beyond 0.5, they become more likely to occur until they're certain, so 100% chance. An example of even chances of occurring is when you flip a coin and you call heads or tails, and if it's a fair coin, so it's not weighted in any particular way, it means that the chance of getting a head is the same as getting tails, and they have 50% chance each. Whereas with a dice, you have 6 different sides, so you have a 1 in 6 chance of getting any one particular number. So in this case, you'd have 1 in 6 chance of getting a 1. Or if we're looking at these 5 balls, and I said, what is the probability of selecting a blue ball? You would have 4 in 5 chances of picking a blue ball. So it's quite likely that you would get a blue ball. Okay, so just to summarize some properties of probabilities. So the probability of an event occurring is always a number that's between 0 and 1. Okay, so it can't be less than 0% chance of happening and can't be more than 100%. Okay, and we represent those probabilities with decimals, the decimal equivalent of the percentage. So that's why it ranges between 0 and 1. Number 2, if an event cannot occur, then its probability of occurring is 0. If an event is certain to occur, then its probability of occurring is 1. And one thing that I haven't discussed is that the sum of all the probabilities of all possible outcomes is equal to 1. Okay, so if you looked at what is the probability that I flip a coin and I get heads or I get tails, when I add those two probabilities up, they must equal to 1, because those are the all possible outcomes. You can't get anything other than a heads or tails when it's a coin. Okay, so let's do some practice questions. These are for events that are equally likely to occur. Okay, it says, in an attempt to gain access to a computer data bank, the computer is programmed to randomly dial phone numbers that are 10 digits long. What is the probability that the first digit being a 1? Okay, let's talk about this. So we're looking at what is the probability of the first digit. That is what I want to know the probability for. And we know that the values of x can belong to 0, 1, 2, 3, and so on, all the way up to 9. So there's 10 different choices for each of the first digits. Okay, if we want to know what the probability of the first digit being a 1 is, that means the probability that x is equal to 1. This is probability notation. The p tells us we want the probability, and then inside the brackets we put what we want to know the probability, of. So in this case, because we want to know the probability of the first digit being a 1, we would say p of x equal to 1. Sometimes, depending on what textbook you might see something like this: probability of first digit being a 1. Okay, same thing, but we've defined X to represent the first digit of our 10-digit long phone number. So we can just use X throughout our solutions. Okay, so we know that there's 10 different choices. And so we have 1 out of 10 or 0.1 for the probability that the first digit is 1. Next, we want to know, what is the probability that the first digit is not a 1? So that means that the probability that X does not equal 1. Okay, you could do this a couple different ways. You could say, well, if it's not a 1, that means that it's either a 0 or it's a 2 or it's a 3, 4, 5, or anything all the way up to 9. So everything except for 1. But the fastest way to assess this problem is to look at the complement. So we know the probability of all possible outcomes is equal to 1. So what we can do is we want to know when it's not equal to 1, so you can take 1 and subtract out the probability of the first digit being a 1, which is 1 minus 0.1, since in part A we calculated the probability of the first digit being 1 was equal to 0.1. So our probability that it's not equal to 1 is 0.9. Okay, if we would have done it the other way, where we added up all the values, you would have got 1.1 plus 0.1 plus 0.1 9 times, and 9 times 0.1 is 0.9. So you do arrive at the same answer either way that you approach the problem. Okay, next we want to know, what is the probability of the first digit being a 3? Well, there are 1 in 10 chances that you get a 3 for the first digit if they're randomly selected, and so it's 0.1 again. And lastly, we have, what is the probability of the first digit being greater than or equal to a 5? So the probability that X is greater than or equal to 5 is, that means that it can be 5 or it can be a 6 all the way up to 9. And when we examine this, we have P of X equals 5, 6, 7, 8, 9. That's 5 different occurrences at 0.1 each. Or you know that that's 5 different values within the 10 that will satisfy P being greater than or equal to 5. And there's 50% chance of that occurring. The probability is 0.5. Okay, looking at question number 2, it says, what is the probability that the computer monitor chosen at random from the following samples has a diameter of 23 to 26 inches? Okay, so we have computer monitor diameters given, and then the frequency within each of those diameter ranges. And we want to know, what is the probability of it being between 23 and 26 inches. So we look at the row for 23 to 26 inches. We know that 11 of them are within that range. So I can write this using set notation. So P of X is greater than or equal to 23, but less than or equal to 26. And we know that 11 of them are within that range. But what we do need to know as well is how many monitors were sampled in total. So if we add up the frequencies, so the sum of the frequencies, that sigma means sum of, that's equal to 39. So 11 out of 39 of the monitors are within that range. And I'm going to round my probability to 4 decimal places. And you'll see that's a pretty typical number of decimal places to round probabilities to when we get to z-score tables. But on an assessment, we will specify how we want your final answers rounded. Okay, so probability distributions. It's a key application of probability to statistics is estimating the probabilities that are associated with the occurrence of different events occurring. And if we have an idea of the probability of a random event, then we can use it to make educated predictions. Okay, In the first problem that we looked at in the practice problems, the numbers were equally likely to occur. So our probability distribution for that one, and I'll write it on the side here, you would have x, so you could have values of 0 all the way up to 9, and then for p of x, because they're equally likely to occur, you would have 0.1, 0.1, 0.1, 10 times. Okay, and if you were to sketch that probability distribution, this would be 0.1 here, and you could sketch it and put your values of x down on the x-axis. So we have p of x up here and x on our x-axis. So 1, 2, 3, 4, all the way up to 9. So you're going to get 9 bars that are all equal in height. Okay, so it's a uniform distribution. We're going to look at distributions that are not uniform as well. Okay, so probability distribution is a table or an equation that links each possible value that a random variable can assume with its probability of occurrence. So there's an example here. We have a table below that has the number of service calls received at a help desk during an hour during the data collected over the previous month. So we have up to 14 calls being received. So 0 service calls, 1 service call an hour, and so on up to 14 service calls an hour. And you can see that the probability of getting 6 calls, and I'll color code these. So the probability of getting exactly 6 calls is given in our table as 0.183. So we would say this is exactly 6 calls an hour. Whereas if we want the probability that x is less than or equal to 2, that's equal to 2 would be shown where p of x is equal to 2, but less than or equal to 2 incorporates the 2 values less than it as well. So we have to add up all those probabilities. It's a probability that x is equal to 0, x is equal to 1, and x is equal to 2. And we can add those up by 0 plus 0.001 plus 0.006 for a total of 0.007. And this would be the statement less than or equal to 2 calls per hour. In the next example, we're asked for the probability that x is greater than 14. So that's not equal to 14, but greater than. And that's everything that's outside of the range here. There's no probabilities given. And so this would be 0. They never receive more than 14 calls. And the probability that you receive less than or equal to 14 calls is the entire chart. Okay, and if you sum the entire chart, it's all possible probabilities. You'll see you add them all up, you end up getting 1. So it's 100% chance that you get less than or equal to 14 calls within an hour. Okay. So data can be displayed graphically, and I gave an example of that above with the uniform distribution. You had a straight line. Looking at this data set, we can represent the number of service calls on the x-axis, number of service calls within an hour on your horizontal axis, and then on the vertical axis we represent the probabilities. If we put these into a histogram, you can see it has a peak around the center. So you would expect, if we were to calculate statistics on this, your mean would be around 7, And if you were to represent this with a continuous function as opposed to a histogram, you end up getting this probability distribution function, which you could, in fact, represent using a mathematical function where you express the average number of calls and calculate the use it to calculate the probability. And that resembles a normal distribution. Okay, so some properties of the normal distribution, and we're going to talk first today about the standard normal distribution. So a normal curve is considered to be the most important distribution in statistics. Many variables tend to have approximately normal distributions, and many statistics assume that populations are distributed normally. So if you can assume that a population is normally distributed, it means that you're able to infer certain things about its population and use the normal distribution to calculate different probabilities. So we're going to talk about the normal curve and its applications in the next class. But in order to consider normal applications, we have to first examine the standard form of the normal curve. Okay, so here's a graph of the standard normal distribution, and you can see that it is a symmetric bell-shaped curve. Okay, and we have various values of z. Sometimes people consider them values of x, but we're going to use z to refer to the horizontal axis on your standard normal distribution. And the readings off the graph are p of z, so the probability of z occurring. Okay. So some characteristics. We know that it's symmetric and it's bell-shaped. We can identify the center of your normal distribution, and that gives us our mean. And in particular, the standard normal has a mean of 0. Then we also know that the standard deviation of the mean is standard deviation of the standard normal curve is equal to 1. And another very important property is that almost all of the area under the standard normal curve lies within -3 and 3. Okay. So what we do is we calculate area underneath this bell-shaped curve to give us probabilities. And we know that almost all the area under the standard normal curve lies between -3 and 3. And because the standard deviation is equal to 1, that means it's between -3 standard deviations and +3 standard deviations. So now we can divide each of these segments up to show 1 standard deviation and 2 standard deviations with values of 1 and 2, since we know the standard deviation is equal to 2, and to the left of the mean, -1 standard deviation, which is -1, and -2 standard deviations, which is -2. Okay, so we label the x-axis with our z-scores. And the total area under the curve is equal to 1. You can see here, so if you calculate the whole area under the curve, it's equal to 1. And that represents the probabilities, because we know that the probability of all possible outcomes is equal to 1. So there's 50% chance, 50% probability that a variable will be less than a mean, and 50% probability that a value will be greater than the mean. So in other words, if we were to calculate the area of one side, under one side of our curve, that probability would be equal to 0.5, and the probability of being less than the mean is also equal to 0.5, so it's half each. So we find the areas under the standard normal curve using a z-score table. Just going to highlight that and then I'm going to show it to you. So the z-score table is available on D2L and it looks exactly like this. You're going to need this to perform your assessment, so to do your D2L quiz as well as your test and to fill in your notes. So make sure you either print a copy of this or keep it readily available on your computer. Okay. And what this table tells us right now, it's just a big table of numbers and seems quite meaningless. But it gives us the area under the curve between 0 and z. So we don't know exactly what z is. We have to look it up based on what we want to know. But it gives us the probability that, of having a z-score between 0 and z. And this will be, the second z there is a number that you want to find. Okay, so that z value, the z scores are all rounded to 2 decimal places. You'll see the first decimal place of your z-score is listed in the vertical column under z, and then the second decimal place is in the row next to your z value. Okay, so I'll go through how to use that in a second. If you are curious, these z-score tables are found using calculus, and the standard normal distribution has a probability distribution function that you can use integration to calculate the area under the curve and give you each of these values. So they're not just made up, they can be reproduced mathematically, but for the purpose of this course, as well as the majority of statistics and probability courses, we can just use this table and take it for granted as something that was solved for us as a tool. Okay. So we want to find the area between 0 and 1.2 in your table. That is the probability that z is between 0 and 1.2. Okay, let's first draw a picture. So you always want to draw a sketch of what you're actually trying to find. And my sketches are never perfect, so you can just use your imagination. Remember that for the standard normal distribution, the mean is 0, and the value of 1.2 is to the right of it. So 1.2, and what we're looking for is the area between 0 and 1.2. We can look up that area on our table by looking up the value of 1.20. So in the first column, we look up the value of 1.2, and we want 1.20, the second decimal place, to be 0, and the intersection of those two will give us the probability that we're interested in, which is 0.3849. So the probability of z being between 0 and 1.2 is 0.3849. Okay. So you'll notice all the z scores in my table are all positive. We don't have any negative z values. But because the standard normal distribution is symmetric, it means that the probability, so we have a property that the probability of z being, I apologize, these are supposed to be just less than. Okay, so of z being less greater than 0 and less than some value, let's call it 1, is equal to the probability that it is greater than -1 and less than 0. So in other words, if we want to find this area, it's going to be the same as finding the area between 0 and our -1 and 0, because our areas under the curve are always positive. It's always a positive value. So even though the z-scores are negative, the actual probabilities are equal area, and that means equal probability. Okay. So the reason I'm talking about that is for the next example, it says, what is the probability that, or find the area, which is the same as what is probability? Probability of x being between -1.20 and 0. So if we draw a picture for what we're looking at, we want the area between 0 and -1.2. That's actually equivalent to finding the area between 0 and +1.20, which is what we found in the last problem. So it's 0.3849, and that's due to the symmetric property of the standard normal distribution. Okay, in the next one, we want the probability for z being between -1.5 and +1.23. And you can see, if we didn't draw a diagram, it'd be hard to know what we're looking at exactly. So we have 0 in the middle, and then we have -1.5, and then we have +1.23. And we actually want the combination of those two areas. Okay, so let's look up 1.23 on our table. Okay, so 1.2, and for the second decimal place, 0.3, and the value of interest is 0.3907. Whereas for -1.5, we look up the value of +1.5. So 1.50 is 0.4332. So for the probability of being between -1.5 and +1.23, you get the area being between -1.5 and 0, and then the area being between 0 and 1.23, and you add those two areas together for a total of 0.8239. So you could actually say that there's 82.39% chance that your z value lies between here, those two values. Okay, and right now I would say that you're probably not finding this lesson to be too applicable, and what we're doing is setting you up with the skills to be able to do more interesting problems in the next set of notes. But without this foundation, you won't be able to answer the other questions, the application problems. Okay, part D, we want to find the area less than -2.13. Again, draw our standard normal distribution. We have 0 and -2.13, and we want the area less than that. Okay, our table only tells us the area that is between 0 and some positive value of z. So we can look up the area between 0 and 2.13. So let's do that now. So I want 2.13. And when we do that, we go to 2.1. And then the second decimal place at the top, we want 0.3, which is this one here. And so you get 0.4834. Okay, that means because of the symmetric property that the area between negative 2.13 and 0 is also 0.4834. But neither of those values are the values that we actually want. We want the probability that z is less than negative 2.13. Okay, we know that the entire left-hand side, so everything less than the mean, is equal to 0.5. So we can take 0.5 and subtract out the probability that z is between 0 and 2.13. So what we're doing is we're taking 0.5 and we're subtracting out the area that we do not want, the area that's not included in what we sketched, and you get 0.0166. So there's 1.66% chance that z is less than negative 2.13 if the original data is normally distributed. Okay. So the last question, we have, I'm going to sketch it out in two different ways. Actually, we want the area that is less than 0.87. Okay, so we have 0. 0.87 is positive, so it's to the right of my mean. And we want this entire area. Okay. So if I break this down using different colors to identify what we know and what we don't know, or start using some of the properties of probability, we know that the area to the left of 0 is equal to 0.5. And we also know, or we can find using our table, the area between 0 and 0.87. So let's look that up. 0.87. So we have 0.8. And for the second decimal place, we want to look at 7. So the value of interest is 0.3078. So the probability that z is less than 0.87 is equal to 0.5, so the entire left-hand side, plus the area between 0 and 0.87, and it's equal to 0.8078.